Hi, everyone. So here's our review of our chapter 3 topics. Just like chapter 2, I did list up the kind of big topics that we talked about in chapter 3. These are included in the practice set I gave you yesterday. So critical numbers, intervals of increase, decrease, maximums, minimums, concavity points of inflection. There's just a sample of those types of problems. So remember that the practice set I'm giving you is not the end all be all of everything you need to know. There was also curve sketching that we talked a little bit about in chapter 3. And then what I want to talk about today are Rolle's theorem, mean value theorem, and optimization, because those were kind of the three big topics that people wanted the most review on. So I'm going to review what the mean value theorem says, and then we'll kind of walk through an example, and then I'll do the same thing for Rolle's theorem. And there's a lot of different types of functions that you can encounter with these. So don't forget that what I'm going over as an example aren't the only types of functions that you're going to probably encounter on the AP test. But if you know the general gist of the theorems, then you should be able to kind of sort through these types of problems. So for the mean value theorem, this theorem, basically, you need to meet two conditions in order for the MVT to work. The first one is that your function must be continuous on the closed interval from A to B. And the function must also be differentiable on the open interval from A to B. So meaning we can't have any breaks, holes, any sort of asymptotes, and we also cannot have any like cusps or corners. If those two conditions are met, then we can say that f prime of some x value c is equal to f of b minus f of a all over b minus a, which in words, remember, means that the slope of the tangent line at our x value of c must be equal to the slope of the secant line on the interval from A to B. So if we look at a quick example of this, we're given some polynomial function. So we know this is a cubic type function. We want to determine all numbers C which satisfy the conclusion of the mean value theorem. So basically what we're looking for is what is this x value where the slope of the tangent line is equal to the slope of the secant line. And because this function is a polynomial function, it will always be continuous and it will always be differentiable because it's not going to have any breaks, holes, or asymptotes, and there's not going to be any corners or cusps. So we know that these two conditions are met, and in order for this conclusion to be met, we want to figure out what the slope of the tangent line is, and we want to figure out what the slope of the secant line is. And it doesn't matter which order you do these in. I'll do the tangent line first. And I'm really looking for, you can do f prime of x, but I'm really looking for f prime of c. So if I kind of imagine all of these variables to be c's instead of x's, this is going to be 3c squared plus 4c. And then minus 1. And then I want to calculate my slope of my secant line. And that's over the interval from -1 to 2. So that means that my A is the -1, my B is 2. So when I set up my slope of my secant line, I'm going to be calculating f of 2 minus f of -1 all over 2 minus -1. And to get the f of 2 value, I'm just plugging 2 back into the original function. So f of 2, I believe, should be 14. If I plug -1 into the original function, I believe that should give me a 2. So my numerator is 14 minus 2. And this is 2 plus 1, so over 3. So 12 over 3 is going to give me a 4. So my slope of my tangent line at x equals c would be 3c squared plus 4c minus 1. And my slope of my secant line is going to be 4. And in order for the mean value theorem conclusion to be met, I need to set these equal. So my f prime of c must be equal to my slope of my secant line. So 3c squared plus 4c minus 1 must be equal to 4. And this is a quadratic, so I'm going to move everything over to one side. So 3c squared plus 4c looks like minus 5 equals 0. what I did was I checked my discriminant on my calculator to determine if this was factorable. It is not. So that means that the only other option here to solve this would be by quadratic formula. So my C would be equal to the opposite of B, plus or minus, the discriminant here ends up being 76. And then all over 2 times A, so 2 times 3. So -4 plus or minus the square root of 76 all over 6. And this is going to give me 2 possible values here. If I do the plus, so -4 plus the square root of 76 over 6, I think that gives me 0.786. If I do the minus, -4 minus the square root of 76 all over 6 will give me a negative, I think, 2.120. But remember that these C values have to fit within the interval that we're given. So this one actually doesn't end up being a value because the -2 is outside of the interval that we're given. So this must be the only C value. So that's going to tell me that C must be 0.786 if I'm using correct AP rounding rules here. And this would be a calculator question. They wouldn't make you obviously do this by hand. So that tells me that the C value 0.786 is the value that does satisfy the conclusion of the mean value theorem for this function. And we said that when we were doing these problems, Rolle's theorem is pretty similar to the MVT. The function must be continuous. So same as MVT above. F of x has to be differentiable. But there was one additional condition that needed to be met with the Rolle's theorem, and that said that f of A has to be equal to f of B. So meaning the starting value has to be equal to the ending value, in addition to these 2 conditions also being met. And as long as these 3 things are true about the function, that's going to tell us that there is a number. We'll call that C in the interval from A to B such that f prime of C is equal to 0. What that means, in other words, or AKA, f of x must have a critical point. And we know that a critical point means that there's really a horizontal tangent in the interval. So if we look at our example here, again, another polynomial function, this time it's a parabola. It's definitely continuous, definitely differentiable. We don't have any breaks, holes, asymptotes. We don't have any corners or cusps. So we know that conditions 1 and 2 are met, but we need to make sure that f of A equals f of B. So I'm going to just make sure that f of -1 equals f of 3. And again, I'm just plugging these values back up into this original function. So I think this will give me, what was that, 1 plus 2 minus 8, which will be -5. Hopefully f of 3 is the same thing. So 9 minus 6 minus 8, I believe, should give us -5. So this is going to show us that f of A equals f of B, in addition to being continuous and differentiable. So Rolle's theorem does hold here. So in order for us to figure out what the numbers C are, well, this one's a little bit more simple than the mean value theorem, because all I have to do here is figure out what my f prime of x is, which is going to be 2x minus 2. And if there's a critical point or a horizontal tangent, I want to take this derivative and I want to set it equal to 0. So if I set that equal to 0, I'm going to get some value of 1. And this could be interchanged for C. So I could have said like f prime of C is 2C minus 2. And then C would have been 1. So this tells me that C equals 1 is the value that satisfies the conclusion for Rolle's theorem here. So the only thing that you really kind of have to think about, if you're not given a polynomial function, think about rational functions, because a lot of times the rational functions aren't going to meet your conditions. So for example, like if I have like 1 over x, this is definitely not continuous everywhere, because at x equals 0, you have a vertical asymptote. So be careful of those rational functions, because a lot of times they're not going to meet your criteria. Depending on what your interval is. Sometimes they'll give you an interval where it will be continuous. So like they'll give you the interval for like this function to be like 2 to 7, which in this case this is only undefined for 0. So from like 2 to 7, it would be continuous and differentiable. So just be careful with the rational functions. Those are really the ones that you really kind of need to worry about here. So that's kind of rules in MVT in a nutshell. I just want to kind of give a quick review of optimization. There are tons of different optimization problems, so please don't take this again as the end-all be-all of problems that you're going to see on the AP exam. Make sure that you go back and look at your notes for all the other types of problems that we did together in class. But there was kind of a general setup of these problems that we wanted to kind of solve. We knew that we were given something, we knew we needed to find something, and then we needed to test the value using the second derivative test. So here we're given this function. We know that y equals 18 minus 3x is our function, and I want to know what the maximum value of the product here is. So what I want to find here is the product of xy, and I'm looking to maximize that. So remember that this expression is going to be the one that we're going to want to take the derivative of, but we want to take the derivative of it with only one variable here. So that's why we're given this expression, because I can take this y equals 18 minus 3x, and I can actually go ahead and substitute it in for this y over here so that I can get an expression that's just in terms of one variable. So I'll shorten that to big P. Bring over the x, plug in this quantity of 18 minus 3x for the y, simplify this. So 18x minus 3x squared. Once I simplify and get this all cleaned up, that's where I want to take the derivative. So I'm looking for p prime here. So p prime is 18 minus 6x. I want to set this equal to 0 to find my critical numbers. So 0 equals 18 minus 6x. That's going to tell me 6x equals 18, which tells me x equals 3. And remember that whenever we get a value for a variable, we want to double check to make sure it is a maximum. So that's where I want to use the second derivative test. Derivative of this, that's what I'm messing up on. So my p double prime would be -6, which again would still be a maximum here. Sorry about that. So my y value here, once I know what my x value is, I want to take my x value and plug that back in to find out what my y value is. So my y would be 18 minus 3 times 3. So y would be 18 minus 9. So y should be a value of 9. So these are my two values. X is 3, y is 9. But then it's asking for me for what the maximum value of the product is. So I actually need to calculate out what that product is once I find my two values here. So the maximum product would be my x times y, so 3 times 9, which would be 27. So that's kind of the idea for the optimization problems. Like I said, definitely go back and look at your notes and look at the other types of problems that we did to help you with the rest of the practice set. And then let me know if you have any questions.